Welcome everyone to the SupportVectors session on paper reading. The paper we are going to read today is Advancing Semantic Caching for LLMs with Domain-Specific Embeddings and Synthetic Data. Quite a mouthful of a title. It seems to be jointly done with Virginia Tech and Redis. So I'll give you some background on this paper and why we selected it. It's actually a surprisingly simple paper, but it addresses one of the very common optimizations that people try to do in the context of RAG. So in RAG, it's very common to ask this question that suppose, so let me give you a small brief on RAG. Just as a simple term, a RAG is a query goes in, RAG is essentially a query, user query Q goes in to, and this is a very simplified version. In reality, agentic RAG with knowledge and complications. It's a little bit more complicated picture, but we'll oversimplify it and we'll say it is made up of a retriever module and a generator module. And the idea is that retrievers are basically made out of, this contains components like semantic index, semantic embedding, vectors in a vector DB. It may contain a keywords-based search DB. You might have a knowledge graph while you're at it. It's very common these days to also have a knowledge graph of some sort, knowledge graph story that you look to. And so when a query goes, usually it is mediated by some agent or some entity that will decide which of the stores to go to. So it's a process of query going through multiple search indices. So let me just call it search index. Indices, index 1, and search index, likewise, search index, oops, sorry, I apologize. Search index A. And from there, they will all, so let me say search index, and they will all produce the top tier results from each of these. They will go into a re-ranker, and out will come the final retrieved results. These retrieved results, which come out of it, will then go into the generator, and the generator, which is usually an LLM, in the simplest implementation, it will be the answer to the query. So you could consider that simply a RAG system is a query in, and out comes a function, which is an answer to the query. An answer to the query comes in, made up of, in a very simplified way, a retriever and a generator. This is a very simple way. Now, it gets a little bit more complex because what happens is that each of these beasts are complicated. The semantic embedding vectors are produced by encoder transformers. So usually you have text encoders. Encoders are also called sentence embeddings. Embedders, or let me just call them, the initial version was called sentence bird, and that word has stuck here, though more generally these are text encoders they produce, and because they are transformer, there is a cost of creating embedding. The query itself needs to be made into an embedding, which has a cost. Then you do the KNN, approximate KNN search into a vector database to find the k nearest neighbors for the query. So just to illustrate the point, what the journey of a query is, a query goes in, it gets into an encoder, which is a bit expensive, but not too expensive, but expensive enough to create a a query embedding vector that goes into a vector DB, which does a KNN search, a proc search, using some sort of a internal storage mechanism, something like a clustering or quantization or some mechanism to make it much faster. And then it returns it. Then you do a reverse lookup of what are the texts that it belong to, reverse to text. And then you get by look up in a dictionary, and then you realize that okay, these are the pieces of text. So you will get the top K search results. And now, in a similar way, your query will go through a traditional search index, a keyword-based search index, and you'll get results. Now, generally what happens is, these are encoder-based tasks. These results, you pass it. Thereafter, this stops K-search results coming from different sources. They finally go through a re-ranker. Re-rankers themselves are encoder-based models. Typically, think of it as BERT, or it would be something like Colbert, or something like that, BERT-like, or Colbert, or something like that. Re-ranker would be there. And finally, it would emit out a nicely ranked retrieval results or search results. And this is only half the journey. Then those search results go to an LLM. You get a search results. And you have a system prompt which says, basically, take the search results and answer the user question. And then the query also comes in here. Query 2 also comes in here, and out comes the answer. So as you can see, RAG is an elaborate journey, and this is actually a simplified view. In reality, most effective RAG systems have many more things going. There are knowledge graphs there are AI agents there, agentic reasoning is taking place, and also, if needed, web searches are taking place. Lots of tools and lots of things come in. Today, a mature RAG implementation is an engineering marvel. But one thing is for sure, it is a whole lot slower than what used to be just traditional vanilla keyword search. For example, going to Elasticsearch and getting search results. A lot is happening. You get a proper answer to your question, not just some reference to documents that you have to read now. Right? But it comes as a price. It's computationally very heavy. So one of the questions that people ask is, can we make it more efficient? And towards that, what people do in most organizations is they start caching the queries. So you are getting this, a queue goes in and an answer to queue comes out from this machine. So you start maintaining a cache of these. And the reason you do that is because experience shows that as much as 30 to 40% of the queries, user queries, are duplicates. And the number goes even further if you take even higher, if you take semantic duplicates, and this word is important, semantic duplicates. For example, you might say, tell me something about type 2 diabetes. And another query could be, I want to understand adult onset diabetes. Now, even though the wordings are completely different, I'll just write it down. Tell me about type 2 diabetes. And the other could be, help me understand adult onset diabetes. Now, we realize that the common words are this and this, diabetes. But so you wouldn't typically textually consider the query Q1 and Q2 to be identical. They are not duplicates of each other. Nevertheless, they are semantic duplicates because they are asking the same question using different words. They are paraphrasing So to the first approximation, you can say that Q1 and Q2 are paraphrasing of the same question of each other, right? And their answer should, in a sense, be the same. So when we do RAG, a common theme is can we not only cache? So instead of doing a hard lookup, so when let's say that a new query comes, Q new comes, and we have a table, a cache of a Q1 answer to Q1, and so forth, Qn answer to Qn, and we maintain a hot cache of it. Let's say at least we recently used cache, LRU cache of some sort of it. It is very tempting to look up this in this cache table. But if you look at this cache table, there may exist a semantic duplicate, but not necessarily an exact textual duplicate, word by word duplicate. And so people have asked this question, can we look up, can we see if there is a semantic duplicate? So how can we do that? Well, the answer is relatively straightforward. What you do is you use semantic embedding itself, which is what you do to create vector, semantic search. Suppose you created a tiny little database cache, which did not put it like this, but instead what it did is it took each query I, encoded the query I to create EI, and then created a cache in effect of EI and the answer to this question. So E1, E2, suppose this was kept here. And now you have all of these embedding vectors of the questions. Then suppose a question comes, a Q new comes. Let's say you have this question, help me understand adult onset diabetes. You would agree that if you look at the embedding vector, it would clearly tell you that the embedding vector E2 is very near E1, right? It would be very, very similar to the embedding vector. Or so you would say that similarity between E2 and E1 would be greater than some threshold value, let's say tau, threshold value. For example, if you're doing cosine similarity, E2, E1, you could say is greater than, let's say, 95%, 0.95, or something like that. Or you can pick a threshold, meaningful threshold. I hope you would agree that that would be the case. And if that is the case, now you have a situation where you can do what is called semantic caching. This is semantic caching. Semantic caching is to say that you maintain a table like this, and if a query comes and its similarity to another query in the cache exceeds a threshold, like it exceeds a certain threshold like this, then you say, why don't I just pick up the answer that was generated from the RAG system for that query and just serve it back? Because obviously a lot of computations went into producing that answer. Right? If I send it through the whole RAG system, it will go through the full-blown retrieval system with its many, many search indices, AI search, semantic search, keyword search, graph RAG, knowledge graph search, and so on and so forth. Agents coming in, re-rankers coming in, finally an LLM producing a result, an agent evaluating the LLM, whether the answer is grounded in the facts or not, in the sources or not, and many, many complicated things. Computationally, a huge pipeline of computations can be eschewed if you could just pick up the answer, because now you know that this question has been answered once. And if you continue to do that over time, what you would notice is there is a pretty high hit rate from your previous answers. For a user query, quite often the answers are all there. Like they say, there's nothing new under the sun. When people come and ask questions, many, many users are asking pretty much the same question, especially in an enterprise domain. Right? The data actually suggests that quite often the same user asks the same question over and over again on different days. So if that is there, then of course one of the primary things that you must put in place as a cost and performance optimization is a semantic caching layer, which people do, or I hope they do. Now there is a question though. This paper pertains to the semantic caching and the encoder that we use, the encoder that was used to take a question query I and to encode the question query I. Now, when you do this, the general idea is that, see, here we are very particular. There is important thing is that you don't want to get the answer to the wrong question. Some question which looks adjacent but isn't, should not be, you don't want to get the answer to that question because that can be extremely annoying. For example, help me understand type 2 diabetes, and then there is help me understand type 1 diabetes, right? These are actually they look near, they both talk about diabetes, but they are actually vastly different diseases. And you don't want to substitute one question with the other and instead serve the answer for the second one. So those are the perils or the dangers of using semantic caching, that you want to be absolutely sure. The precision has to be very high. In other words, the true positive over true positive plus false positive. In other words, if you say that this particular query Q1, Q2, Q3 in the past are the nearest queries, you want to make sure that they are all genuinely related or identical to the question the user is asking. So that is important. So in other words, in this game, precision is the metric of choice. You want to make sure that there is very high precision. Recall also matters. Recall just says, okay, if there is a question that is a paraphrasing of the question the user has asked, it better show up in the search results of the of that retrieval process, like similarity, semantic from the semantic cache. That result better surface. Right? So, but precision takes more importance. Now, with that as a backdrop, let us read this paper and see what it is trying to say. If anybody has a question, please ask me, but I'm assuming most of you are somewhat familiar with what retrieval-augmented generation is and the considerations, practical considerations that I brought up.
Well, so far good, actually. Thank you.
All right. So with that, let's read this paper now. This paper's abstract says, this report investigates enhancing semantic caching efficiency by employing specialized fine-tuned embedding models. So what they want to do is a specialized fine-tuned embedding. Semantic caching relies on embedding similarity rather than exact key matching, presenting unique challenges in balancing precision, query latency, and computational efficiency. So that thing, let us unpack. I think we have done that as we realized that if we are not precise, if your semantic caching doesn't yield precise, if you ask, help me understand type 1 diabetes, and it returns you answer to type 2 diabetes, you lose. Obviously, that lack of precision is horrendous. At the same time, if you don't do semantic caching at all, then when two questions which are paraphrases of each other will be treated as different questions, and so the second question will trigger off the same entire RAG computation pipeline, which means that there will be query latency and there will be a computation cost. So the whole point of semantic caching is to optimize or bring about computational efficiency without a loss of precision. I suppose that statement summarizes it. So I'll just write it down. Goal is improve computational efficiency without loss or retaining high precision, your answers are still, the answers that you serve are precisely the answer that you would have liked to serve. We propose leveraging, and now what this paper says is, we propose leveraging smaller domain-specific embedding models, fine-tuned with target real-world and synthetically generated data. So the rest of the paper, actually, the key idea is that, why don't we take small models, because we are just trying to train a semantic cache and domain-specific semantic cache. The two domains, so it takes the domain of Cora, which is a general domain, and then it takes medical domain. But generally speaking, its key idea is that if all you're doing is embedding questions, you can take small models and you give it only one task. Be able to tell the nuances between questions apart, to know when a question is a paraphrasing of a prior question, and when a question is actually subtly different from a prior question. Right? And that is the game you want to play. And their main thesis is, you can play that game effectively with a small fine-tuned model. That's what they're saying. So we propose leveraging, I'll repeat it, we propose leveraging smaller domain-specific embedding model, fine-tuned with targeted real-world and synthetically generated data. Now comes the results part. Our empirical evaluations demonstrate that compact embedding models fine-tuned for just one epoch, and this is interesting, and how is this possible? We'll see. Just one epoch on specialized data sets significantly surpass both state-of-the-art open source and proprietary alternatives in precision and recall. Right. Moreover, we introduce a novel synthetic data generation pipeline for semantic cache that mitigates the challenge of limited domain-specific annotated data, further boosting embedding performance. Our approach effectively balances computational overhead and accuracy, establishing a viable and efficient strategy for practical semantic cache implementations. So that's what this paper is saying. Now I'll go over this paper quickly, because 2025, we all know how these things work. So introduction, only some part of the introduction I'll read. Large language models are rapidly becoming integral components, etc. The fact is that it just speaks to the fact that it is all very, very expensive. And here they go on to say that declaring a cache hit if the similarity between two embeddings surpass a predefined cosine similarity threshold. So this is the idea that we were talking about here in white color, that if your similarity exceeds a certain threshold, then you do that. Now, how would you do that? The method is actually very simple. What they do, and I won't go through line by line in the method, but I'll just explain. What they do is, they say, first, so the approach, let me just decompose the approach into two things. They say, let us take a data set. So approach. Let's take a public data set. They take two data sets. DS1 is Cora QA data set. The second data set they take, data set number 2, that they take is a medical data set. It's again a CAT, medical data set. Now, as you know, medical language is quite nuanced. It's a dialect that pretty much only the tribe of medicos understand fully. The rest of us find it a bit bewildering, and nuances matter. Like I said, type 1, type 2 diabetes are entirely different beasts, even though they use the same words. So they take these two data sets. Now what do they do? These data sets come as Q, question, a question, let me just pose it like that, a question and an answer. So what they do is something quite interesting. They go to an LLM, bring an LLM, right? And you assume a good one. Right? Give it the task, give it a prompt, given Q, create a paraphrasing a few paraphrasing if you want, a paraphrasing of Q using different words, phrases, etc. So you're now using different words or phrases. And they give you the prompt. Here is the prompt. It's worth reading. Prompt for paraphrase generation. And they give you an example. Let's say that you have an original query. What are the best ways to reduce stress? And they give you, how can a person, the paraphrasing queries are, a paraphrasing of it is, how can a person effectively manage stress? What strategies help in reducing stress levels? Now, you would agree that these are semantic duplicates, right? That's the idea, the paraphrasings of the query. So here's the prompt that they use, which is, again, now we all know prompting, and so it should come not as a surprise. You are a helpful medical expert. Given a medical query, generate two distinct but related queries that explore different aspects of the topic. Guideline. The new query should be related to the original, but focus on different
topics, perspectives, or medical context. They should not be simply rewordings or slight variations of the original. Consider different patient populations, alternative diagnostic methods, treatments, or physiological explanations. So example.
How to reduce stress. And distinct queries are, and it gives you an example. These are two distinct. Original query. Another example is a 61-year-old woman with a long history of involuntary urine loss during activities like coughing or sneezing, but no leakage at night, undergoes a gynecological exam and Q-tip test. Based on these findings, what would cystometry most likely reveal about her residual volume and detrusor contractions? Distinct queries are, how does the Q-tip test help differentiate between stress urinary incontinence and urge incontinence? Context diagnostic techniques. Second question is, second paraphrasing is, what are the treatment options for stress urinary incontinence in post-menopausal women? And how does cytometry aid in management? Context, treatment, and management. I suppose these are things only the medicos would understand, but I suppose that's that. Now generate two distinct queries for this input, original query, return, blah, etc. And so you can imagine that this prompt is exactly the system prompt that you would have written, some form of it. This is to generate similar ones. But at the same time, you generate, and what is more interesting is a similar one is not a surprise. You do, okay, just paraphrase it. But you do prompts for non-duplicate. Sorry, actually, I take that back. Original query. This is for prompts for paraphrase generation. This is actually the interesting part. This was for non-duplicate, distinct query generation. You are saying that given let me be clear. Given a query, ask another question that is not a paraphrasing. Actually, that is a slightly different query, but very, very close to it. In the language of loss function, you would say, you're trying to create a hard negative, something that looks suspiciously like the original query, but is not. Right? So they give this example. How to reduce stress and how can athletes manage stress during high pressure competitions? So as you can see, how to reduce stress is about you and me. How can athletes manage stress during high pressure competitions is not about you and me, unless you believe you're an athlete. Right? What are effective stress management strategies for children with ADHD? So you notice that they are all about stress management, but the context has changed, right? So these are hard negatives. The word hard negative implies that it looks as though it's related, but it isn't. And you really need a machine to be trained to tell the subtleties apart, the nuances apart. Right? In the same way, this query about the woman and the distinct queries are actually two hard negative examples. These are non-duplicate or distinct query generation. Means they seem to be very, very close, but they are not. So now what do we have? The point is using an LLM for every query. So using an LLM for every query QI, you will be able to generate a positive example, PI, one or more positive examples, and you would be also able to produce hard negative examples, isn't it? Hard negatives are the ones that on a very superficial level seem to look alike, but actually are asking subtly different questions, or nuances are different. Right? So you can use an LLM to produce this data. Now, why would you want to produce that? That has to do with the contrastive learning. So I'll just sort of give you a review of what contrastive learning is. See, in contrastive learning, what you do is you need to train an encoder, and in contrastive learning, you give this problem. You say to the encoder that I'll give you, well, we think in terms of triplets intuitively, though in reality, you use a softmax function, but I'll give you both the versions of it. Let us say that you have a query, QI, and what you do is you pick a paraphrasing of it, which is similar, right? So this one is easy. What you do is you try to minimize, you try to maximize the similarity. Let's say you can take cosine similarity if you want between QI and what you know is a similar item, isn't it? And you want to minimize the same similarity between QI and the hard negative I. Does this make sense, guys? It is very obvious that in the embedding space, what you're trying to do is you're trying to make sure that if QI, E of QI lands here, then then the embedding vector for E of SI, embedding vector should be nearby, very small, very similar. But you want to have that something that is a hard negative, which seems to look similar but isn't. You try your best to push it out. In the ideal case, you want to push it out as much as possible, right? Hard negative, you want to push out to a point here. Right? You would want to do that, isn't it? And so you craft a loss function. This is called the contrastive loss. This belongs to a family that is often called the contrastive loss function, where you apply this kind of a reason. Right? This is often sometimes presented as distance also. What you say is minimize, maximize the distance, the distance between negative d minus, which is the distance between qi and hard negative I, and minimize the distance is the opposite of saying the previous one, similarity, qi and similarity I, right? Contrastive loss function. And then there is another variant of it, actually, which uses a slightly different trick. What it says is that you can take e to the similarity between qi and similar I, and then, and this is the summation of e to the similarity between qi, hard negative I, right? Always take the hard negative I, not all the other things that you can think of, or all hard negatives that you can find like that, and e to the sim of course, QI. So this is just a normalization of the partition function at the bottom, but you do that as your loss function. So those of you who are familiar with the different kinds of loss function, you would probably remember things like this. But the main point is, think of it in simply like this, right? You want to push, geometrically is very simple. You want to put QI and SI closer to each other, and you want to push QI and the hard negative as far away as possible. So this gives you a training method, and that is the reason that you use the LLM to produce this paraphrasings for you that we saw. And that is the gist of the paper. That is the gist of the approach they use. They use an LLM and they go to the Cora and to the medical database CAD, and they produce lots of similars and dissimilar. And then what they do is they take a modern, like an encoder. So as many of you know, last year, Modern Bird came out. Modern Bird was a revision. The original Bird was beginning to show its age, right? And Bird had evolved to all sorts of things like Roberta, Diberta, Distilbert, etc., etc. And then somebody said that let's do one thing. In fact, a group of researchers said, let's do one thing. In the LLM, there has been so many innovations, especially on the decoder side. On the generator side, there has been rotary embedding, there has been context length has become bigger, there is a flash attention, and so many new innovations have come in. So let us collect all of those innovations and all the optimizations that have come in and bring it together. Right, and it has sort of local attention, global attention, interleaving, even the loss function, even the activation function has become a gated GLU, right? Gated GLU function, whereas the original one was different. So all of it put together, you can do lots of optimizations, gather all of them and put it, backport it to the BERT architecture. And when you do that, you end up with a 149 billion parameter, which by today's standard is a very tiny model. 149 million or billion, if I remember right, it's million actually. 149, I would like to say it's just million parameter modern BERT that comes out, and you use this modern BERT and do contrastive learning on it. Let's redo the whole thing and see what happens. Right? Yeah. So 149 million parameter modern BERT by today's standard is minuscule, as you would agree. The way the LLM sizes go. So and that's the main contention. You can take a modern BERT, a tiny model, fine tune it with this sort of data that you have created of paraphrasings and hard negatives, apply the contrastive loss, and now you can do a semantic caching in the sense that we talked about. So that's the core idea, guys. I will just pause here in case anybody wants to ask a question. And that's the methodology. And after that, we will look at what is the result they got from all of this.
So, I mean, the expectation is that we have these data, right? Or this, I mean,
No, you create the data. See, this
database.
Yeah, Cora data set exists of question answer. And so if the questions exist, all you have to do is create paraphrasings of the question using an LLM. Do we get that? Sure.
Yeah, I got it. Yeah. So basically, yeah. So we just take the that is a synthetic part of it.
Yeah, that is it. And now in this paper, actually, somewhere there's a subtlety here, which, so by the way, their model, they call it Lang cache embed. Whenever you see Lang cache embed in the paper, it means they're fine-tuned modern BERT for this purpose. So clearly you see, now they're looking at a few metrics. So let me just go over precision. We all understand what precision is. Precision is, see, in precision, you threshold it. You say it is a true positive over the ones that you mark as positive, right? So suppose there is a question and you go and look up into the cache and you semantic cache and you come back with some other question. Was that really similar to it? The ones that you brought from the cache, or was it actually not a true positive? It was different. So what do you want? You want high precision. So the question is, was it similar or not? Ultimately, machines produce a probability, right? So let me put it this way. See, a machine will just say probability that given a query QI and some candidate J are similar or not. So it will produce a number that belongs, it's a real number. Actually, it belongs to the interval 0 to 1, right? It's a fraction. It will produce a fraction. Now what you do is you always put a threshold, typically 0.5, 50%. If it says 50% chance that the query and this cached candidate are the same, you say it's a hit. Greater than 50% is a hit, miss otherwise. You say it's not. So you will go and pull all the candidates where the probability of similarity in your cache is greater than 50%. So now the question is, suppose you brought back candidates, 4 candidates. How many of them were actually paraphrasing? So that would be the true positive rate. True positive over 4, which is the total number of positives that you identified, is precision. So just giving you a recall, reminding you what the word precision means. But precision is for a specific threshold, implicitly specific threshold. Here, they assume the threshold of 0.5. Clearly, you can see that their model does outstandingly well. In this case, which particular data set are they looking at? They're looking, I believe, at Cora, but they haven't mentioned it. Evaluation of different embeddings on medical data set. So in this particular case is the medical data set. So as you can see, their precision is pretty high, 92%. Whereas without fine tuning, modern BERT, you notice that it went from 78% to 92%. So what does it prove? It proves that fine tuning worked. It did bring improvement. And when you compare to other big models, see GTE, Quen, and all the other models that are mentioned here, these are all well-known models, OpenAI's text embedding, Amazon, etc., Cohere's. These are all commercial and open source state-of-the-art models. And what they show is a tiny modern BERT fine-tune beats them all. Right. Likewise, recall. What does recall says? If you know that there are, like if you plant in your cache, let's say 2 real paraphrasings of this question, and then you say, okay, go get me that, and 4 answers came out. You want to make sure that the 2 that you want did actually come back. How often it came back is a measure of how often the real answers did come back is a measure of recall. F1 is simply the harmonic mean of precision in recall. And accuracy is like, well, okay, accuracy is the error rate and so on and so forth. But now there is another thing called average precision that perhaps needs a little bit of explaining in case you're not familiar. What it says is, if you make a precision recall curve, let me take a color. Let's take this. If you make a precision.
Recall is without hitting the LLM, or how does it like just?
No. Recall is a machine learning metric. No? So suppose you imagine that you are searching into a data, any kind of thing, any kind of a storage. Let's say that there are 2 answers that are correct answers to your question. You may get whatever number of search results. Right? Let's say you got 10 search results.
Okay. Yeah.
Now the question is, did those answer 1 and answer 2 actually come back or not? If they came back, you have perfect recall.
Oh.
If not, if one of them came back, 50% recall. If none of them came back, 0.
Yeah, where it came from. Okay.
Exactly. So it's a measure. So I'll give you a very common sense perspective on recall. See, people do this psychological test on memory, right? By the time you begin to reach my age, you'll notice that your friends or your younger relatives will start playing this game on you. They'll tell you a list of words like cabbage, aeroplane, horse, scooter, and so forth. Totally random 10 words, let's say. Then the conversation will go on. Then 1 hour later, they'll ask you, okay, tell me what were the 10 words we told you. So out of 10, let's say you can correctly recall 6 of them. So what is your recall rate? 6/10.
Got it.
That is literally the intuitive meaning of the word recall, right? And now, precision and recall are something interesting. The precision recall curves, let's say that you have this. Area under the precision recall curve matters because if you have a high precision, means you always can tell the positive as the positive, right? Sometimes what happens is recall is low because you have to be absolutely sure to make sure you don't have a false positive. So you will be very hesitant in providing an answer that you're not sure of. But as you increase the recall, as you try to, because you become more optimistic and you begin to increase your recall, then what will happen is you will end up with false positives, so your precision goes down. So the area under the precision recall curve is called average precision. What average precision measures is, in a sense, how well a retrieval system is able to stack rank, can rank the queries by their relevancy. Suppose you have a question, the other similar questions that it finds out, how well it has correctly ranked them. Right? So this is again a thing that is sort of endemic to all of machine learning, especially the retrieval, the search industry, but that is the concept of average precision. So I'm mentioning it just in case you're not familiar with these terms. So you can see that the average precision of this machine is of this new model is very high. It is 97%, and it went up from 92% to 97%. If you just use modern BERT, it would be 92 otherwise. And it beats all the state of the art just marginally. If you notice that 96 was the link embed Mistral. Mistral was producing about 96%. So, well, it didn't beat by much, but it does. Let's just say that this approach compared to Mistral, etc., which are big models, fine-tuning modern BERT using this approach, in the very least, achieves the state of the art. And very, very, very modestly, it beats the state of the art also. That's the core message of this paper, right? And that is it. That is what it is trying to say all over. And this one should. Now, one of the things that happens is, does catastrophic forgetting take place? You would imagine, yes. If you, for example, train a machine to do very well on medical domain, there is no such thing as a free lunch. It has become very good on medical, so it will start slightly doing poorly on Cora. So that on the Cora, the other data set. So it's understandable, and what they're basically, and then so there are ways of preventing it and not doing too excessive updates and so on and so forth. But we won't do that. That is common sense. Catastrophic forgetting is always something that you have to watch out for and do a controlled fine-tuning. So there is nothing special with this fine-tuning. It is the way fine-tuning works. Now, so how does it all work if you look at the overall result? Because in this game, average precision and precision are the key metrics. We should focus on this, how well this machine does compared to, this model does compared to all the other. And as you can see, both in the precision column and in the average precision column, it does quite well, right? If you just do purely medical, synthetic medical data and so on, so there are a little bit of nuances here and there that you talk about. And what they are basically saying is that by using such a tiny model, you hit the sweet spot that is mentioned here. Namely, you have very high average precision for actually a tiny model. Right? You notice that this model, modern BERT fine-tune, has very high average precision. But look at the embedding generation time is a measure of size of the model. If the model is small, there are fewer computes in the forward pass of the encoder. Embeddings come out quickly. The latencies will be low. And that's what you want. You want, what is the ideal goal? You want very low latency and very high precision. And this basically this plot says, yes, it manages to achieve that. right? And that is it. That is the end of this paper. So when you look at this paper, you cannot help wonder that, see, it's a simple idea. The main thing that they are saying is, it is good to have a semantic cache. In fact, why would you not have, when you have a mature RAG system? You should always have a semantic cache. But why do people not have it? They don't have it because they're so afraid that a question comes, but it ends up answering an adjacent question which is not relevant, right? So a question that is in a nuanced way is a different question, but to the encoder may look like the same question. And what if you make a fool of yourself by answering the wrong question? Like, for example, tell me something about type 1 diabetes and tell me something about type 2 diabetes. And what if the machine ends up giving the wrong answer? So people sometimes avoid semantic caching, but I suppose techniques like this are a huge step forward, or some progress towards encouraging you to use semantic caching. Because if you do use semantic caching, and if you can get away with it, if you can have good precision, average precision, then what it means is that you save a tremendous amount of compute in your system. Now, as you know, RAG is deployed on an enterprise scale in most companies now. They take a pretty heavy query load. It is like, see, it is no surprise that this paper has come out of Redis. If you think about it, what is Redis good for? The primary use case of Redis is cache, high performance cache. And if you remember, even with Quora itself, you can have a user query go straight to Quora, the database. And I believe at one time they were using, was it Quora or was it Stack Overflow? One of them was using SQL Server database, and it was getting computationally heavy, and they were thinking of buying lots and lots of database servers and instances and licenses, which would have been expensive. And what they did is they put a Redis layer. This is the history of this. They put a Redis layer, and then they realized that they can take vast web scale traffic, and most of the hits go to Redis rather than actually penetrate through to a database query. Very few queries are fresh queries. Most queries are duplicate queries. And so you could get the answer straight from Redis. So this is, in a way, a logical progression of the same thing. The search world has now become the RAG world. And so what was Redis, pure Redis key value lookup, is now a semantic cache, right, within the RAG system. And so it is, I suppose, appropriate that people who are in Redis are thinking about it quite a bit. And they have been, and with Virginia Tech, they have been instrumental in writing this paper. So this is it, guys. Any questions?
No, I just sorry about I don't know about semantic cache, so my questions might be very basic. So I mean, where do you store? What is the storage for semantic cache? Is it like
the little vector database? Yeah, just store it in a vector DB.
Oh, it's a vector DB itself. Okay.
That is right. You can see, here is the thing. Generally, what you do is you can keep it purely in memory as a vector DB, or you can persist it to disk and use it depends upon how big you want to create your. The main point is, even if let's say that you have a massive semantic cache, because you're caching a lot.
Okay.
It's still over, not just in memory, but so suppose it was just memory, then of course is gold. You're golden. You get a hit, lightning fast you return, sub-milliseconds you can return, because you look up the answer and you just serve it back. It becomes almost like a Redis kind of use case. On the other hand, even if it is a vector DB, let's say you're using Qdrink, what are you doing? You find a similar query, but because you have stored past queries and their answers, let's say in Redis or somewhere, all the past queries are there. The moment you identify a query is similar to a past query semantically, now what can you do? You can just serve back the answer of the past query. That's it. Right? So what semantic cache does to the world of RAG is what Redis used to do to the world of ordinary queries.
Yeah, Asif, this is Krishan. So it's a wonderful paper. Thank you. I have two questions. One is, we know sometimes, even the small history and context would change the results. So how does this paper address that? In other words, the query QI that you mentioned, right? is it in consideration with the context and history? It's able to cache, or I'm just wondering
Yeah,
about that.
yeah. At this particular moment, right, in its purest form, it is context unaware query cache. But now let's bring in
Okay.
context.
Okay.
What we do is
Mm-hmm.
people. So imagine that the query, by the time a query comes to you, what has happened is some agent has already injected the context. So what you are getting is the query with the context injected, right? So this, what happens if the
Yes.
same user or another user in the same position, let's say another your colleague in the same department, same role, is asking the same question or similar, semantically similar question. So the context injection that has taken place on the query is identical, therefore. And so your
Mm-hmm.
augmented query, what you're doing at that moment is you're doing a semantic caching of the augmented queries, right? So the
Yeah.
idea is that, see, it is one technological piece. Now the thing is, how do you use it for your situation where you're doing context augmentation of the query? So you can do that, right? See, it comes from a data. Somewhere in the paper, they mentioned yet another research paper whose finding is surprisingly duplicate
Mm-hmm.
queries come often from the same user,
Yeah.
right?
True.
Yeah. And so at least that
Thank you.
case you
And
can.
what do you think about all the? Yeah. Sorry. The second question is, what the frontier LLMs, right? All the OpenAI and stuff like that. Are they doing caching? And now, is this today's paper anything relevant to that?
See,
In terms of,
obviously,
I'm talking about the LLM side. Sorry.
that is right. So see, we have to remember that frontier models are not models, they're systems. When you use ChatGPT, when you use Anthropic through a user interface, you're not just hitting an LLM, you're hitting an entire system. Now, obviously, their architecture is not published, so so whatever we say is a guess. But I bet you that they have some some form of queries or some answers pre-cached, because most users tend to ask very similar questions. See, today if there is a news, let's say a typical situation. Recently there was an earthquake somewhere, and it was in Asia, and it was a pretty devastating. So you can imagine that it is in everybody's mind, and people go and ask questions about earthquakes and how much, what does it do, and what does a Richter scale 8 mean or Richter scale 7 mean. So it does make sense that when a frontier model answers a question, it is computationally so expensive that it behooves them to maintain a semantic cache. They must be doing it.
Okay. Thank you. Thanks, Asif.
Yeah. Any other questions, guys?
So I mean, like, for example, I mean, like, let's just. So if suppose like somebody says, what is the cure for diabetes if someone is more than 60 years old? That would.
Yes.
So I mean, that question doesn't exist. So like, I mean, does it like combine two things or it doesn't, right? Like,
No, it does not. It's not additive. So
okay.
one of the things that you don't do is saying that, see, I can decompose the question into two questions, and now those two questions, for example, multi-hop. So for example, you see, semantic cache, right? It solves a simple problem in a very atomic way. It says if your questions are near semantically equivalent, it will solve it. But what it won't do is a multi-hop and or any kind of thing that, hey, this answer maybe is more than enough to answer a slightly different question, because that question is a subset of this question or something like that. No complications. See, caches are very simple things in
Yeah.
general.
I mean, you already mentioned like it's more like a radish cache for your data.
Yes,
It's like it doesn't
exactly.
have a lot of intelligence or anything like that. It's basic
And you don't
domain.
want that.
Yeah.
You don't want that, because these things have to be, see, for it to be efficient, right? Latency you're trying to reduce, and computational cost you're trying to reduce.
Yeah.
So obviously you want to achieve your results very quickly, and you don't want to inject a tremendous amount of compute intelligence into it.
Makes sense.
Any other questions, guys?
Sorry, I might repeat the again. Like, there is something called when you show the score, right? The metric.
Yeah.
There is like F1 score, right? Like, can you just reiterate that?
Oh, F1 score. F1 is, see, what happens is that when you increase, see, in any system, right, there is two opposite forces at work. These are precision and recall. Precision is, now I hope I don't get my point, over positive. You declare some cases to be positive. There's a classifier. Its job is to tell whether you have, let's say, some patient has diabetes or not, right? And the machine declares 10 people as diabetic. So there are 10 positive cases. Then subsequent, what is the ground truth? How many of them really have diabetes? Those are the true positive numbers. So let's say 6 people had diabetes. So 6 over 10 is the precision, right? Now recall is literally, suppose you know that there are 16 people who really have diabetes, and you ask the machine to find all the people who have diabetes and give you a list of, let's say, I don't know, top 50 people it suspects has diabetes. Now the question is, how many of those 16 people actually showed up? True positives actually showed up in the search result, right?
Yeah.
That is, so now what happens is a machine has to fight two opposite forces. To increase recall, what it can do, it can go trigger happy. Even the slightest suspicion of diabetes, it can say you have diabetes.
Yeah.
Right? But then if it goes trigger happy, recall will increase because it will be able to more likely identify the diabetic cases. But what will be wrong? It is trigger happy. It has created a lot of false positive, isn't it?
Yeah.
False positive plus true positive, right? So what will happen is this denominator will increase. This will start going up. If you increase recall blindly, then your denominator will start increasing, and so your precision will go down. So between precision and recall, there are always opposite forces at work. Yeah? And so at any cutoff, at any given cutoff, right, threshold, there will be some value of precision and some value of recall. So let us say that the precision is P and the recall is R. You want to have the best of both the worlds, ideally, isn't it? So when you really don't, see, sometimes you want to increase precision, like in the case of search. Precision is more important than recall. Let me give you another way of understanding this. Suppose you have a screening test. You go and, as you grow older, people screen you for all sorts of things, for prostate cancer, for breast cancer, etc., etc. What do you want? You want to be trigger happy. The first screening test, even the slightest suspicion that you have cancer, you want to declare needs further screening, right?
Yes.
So there you need high recall. You don't want to miss a good case, right? On the other hand, when you're dealing with search results, like in our particular case, it will be very annoying. You ask a question, but it comes back and says, hey, there is another question whose answer. This question has been answered in a different way already, right? Because there's a paraphrased question present. And it turns out to be false. That will be a disaster. So there you want high precision. So on a situation by situation, you want precision or recall. But if you don't care for either, like let us say that all you care for is that both the numbers should be good enough. Then what you can do is you take the reciprocal, you call it F1. F1 score is something called the harmonic mean of, you remember harmonic mean? The arithmetic mean of two numbers is p plus, like a plus b over 2, right? Harmonic mean is the reciprocal, of the two, right? So that is the harmonic mean. F1 score is simply the harmonic mean. Right? Now, why do you take F1 score? Why not just take accuracy? Accuracy doesn't work in many situations because accuracy is actually in many situations doesn't work. Whenever there is a class imbalance, it doesn't work. I'll give you an example. Suppose you have a machine that tells whether people have diabetes or not. Now, let us say that you're talking about children. Children don't usually have diabetes, right? There will be maybe 1 in 100 child who has childhood diabetes.
Yeah.
Right? So suppose you make a fake machine, and that machine declares everybody don't have diabetes, don't have diabetes, don't have diabetes. What is the accuracy of the machine? How often was it wrong? Only 1% of the time, isn't it? So its accuracy is 99%. But
Yeah.
its precision is a disaster.
Yeah.
That is why people don't like, and they prefer the F1 score as a better metric, because whenever there is a class imbalance, then F1 score will tell you whether your model is still good enough. Right? That is why people use the F1 score.
Thank you.
Any other questions, guys? All right, guys. So in that case, if there are no other questions, thank you for being part of the SupportVectors learning community. I hope to see you next week. As a reminder, our courses are starting. Just as a reminder, if you will please entertain my little spiel for SupportVectors. We do offer a lot of training in artificial intelligence, especially generative AI, and we have a website where you can go and see the courses. 4 of our courses are coming up. They are Foundations of AI, Neural Nets, Large Language Models, AI Agents Bootcamp, and RAG. RAG and AI Search is starting. That's also a bootcamp. These 4 bootcamps are starting in June. So if you are interested, please do enroll. These are intense bootcamps. We cover a lot of territory over a space of 4 months, 3.5 months actually, 14 weeks, and we really make you an in-depth master of these topics. So if you do want to learn these topics in great depth, please do join this bootcamp. Any final questions before we close? All right then. Good night, guys.